morning, this is B. Naresh, working as assistant professor in EC department. Today's topic is construction and principal operation of JFET. So, up to this, we identified the two types of the transistors. One is bipolar junction transistor, another one is the field effect transistor. If you observe the BJT principle in a bipolar junction transistor, the conduction depends upon both the charge carriers, that is majority charge carriers as well as the minority charge carriers. But coming to this field effect transistor, it is also called as a FET, in which the current depends upon the how much electric field is applied between the terminals like gate and source. So based on the applied electric field, it allows the conduction across this transistor. Hence, this transistor is called as field effect transistor. And but coming to this field effect transistor, if you compare with a bipolar junction transistor, but in the case of bipolar junction transistor, the current or conduction depends upon both the charge carriers, that is majority as well as the minority. But coming to this field effect transistor, it depends upon only the majority charge carriers. Hence, the FET is also called as a unipolar device. So hence, here it is represented as the FET acts as a unipolar device. And based on the construction, like if you want to observe the BJT construction, if you want to design a BJT or a bipolar junction transistor, we take it as either NPN transistor or a PNP transistor. So based on the doping levels of the materials and based on the construction of the transistor. Similar to this field effect transistor also, based on the construction, here the FET is classified as two types. One is called as junction field effect transistor. It is also represented as JFET. Another one is metal oxide semiconductor field effect transistor. That is represented as MOSFET, where M indicates the metal, O indicates oxide, S indicates the semiconductor, and FET means field effect transistor. Hence, this type of the transistor is called as metal oxide semiconductor field effect transistor, and it is also called as insulated gate field effect transistor. Hence, based on the construction of the FET, we defined as two types of the JFETs. One is junction field effect transistor. It is also called as JFET. Another one is MOSFET, that is nothing but metal oxide semiconductor field effect transistor. And similarly, depends upon initially we discussed that in a FET, the conduction depends upon only the majority charge carriers. So means that based on the doping levels, if you consider the N type, the majority charge carriers are electrons. If it is a P type, the majority charge carriers are holes. And based on this majority charge carriers, the JFET or a junction field effect transistor is again classified into two types. One is called as a N-channel JFET. Another one is the P-channel JFET. And here we represent it as the N-channel JFET means the majority charge carriers. We know that in N-type material, the majority charge carriers are electrons. Hence, in this N-channel JFET, and the conduction depends upon the majority charge carriers, that is electrons. Similarly, if we consider while doing the construction of this JFET, if we consider the P-channel JFET, and we know that in a P-channel, the majority charge carriers are holes. Hence, the conduction depends upon the holes, that is majority charge carriers. And coming to this construction, how we are representing this N-channel JFET construction and why it is called as the junction field effect transistor. To understand this principle and the construction of the JFET, let us consider a piece of semiconductor bar, and this bar here you can write for this N channel, it is taken as the N type bar. So hence this N type bar is represented as N channel. For this case, one end is a electrode is connected. That electrode here it is called as drain. It is represented by the D. Another side, one electrode, that electrode is connected as a source. It is represented as S. If we taken as a N channel, this is the bar, and opposite two ends, it is doped with opposite material, and these doping concentrations are very high compared with this N type material, and we need to take opposite doping material, hence this is called as a P plus. So two ends is represented with the electrodes, one electrode is represented as a drain, another electrode is the source. Opposite two ends is doped with a heavily doped opposite material, and that is compared with the channel. Hence, we here consider the N channel, hence the opposite doping material we taken as a P plus, and internally these two are shorted, and externally it is connected to one electrode. That electrode here it is called as gate. It is represented as G. So this is the construction of the N channel JFET. And why it is called as the junction field effect transistor means, when we take this piece of semiconductor, the piece of semiconductor it is represented as N channel, and opposite we are doping with the P plus, hence we are interconnecting this N channel and the P plus material, hence it forms the junction. And due to this region, this type of the construction is called as junction field effect transistor, and it is belongs to N channel. Why? Because of that the length of the piece bar, and here it is called as the channel. And this channel is made up with a N type material, hence it is called as N channel JFET. So hence I shown this representation of N channel, and whatever the channel, either N channel JFET or a P channel JFET, in this FET it contains the three terminals. One terminal is represented as the source, one terminal is represented as a drain, and one terminal is represented as gate. Hence, we have the three terminals: source, drain, and gate. And another one is the channel. So these are the three terminals along with one channel. Either the channel is either N type or a P type. So coming to here, the source means it gives the charge carriers to allow the conduction. The source is always gives the charge carriers to allow the conduction. And based on that, so here we consider as a N channel JFET, and for this N channel JFET, the source and the drain is also made up with a N type. Suppose if it is a P channel, the source and the drain is made up with a P type. But here we consider as a N channel JFET, hence the source and the drain is made up with a source. Let us consider the source is N type, hence the majority charge carriers are electrons. So these are the majority charge carriers. And the source, it gives the charge carriers to allow the conduction in this FET. And a drain, coming to the drain is used to collect the charge carriers from the source. Whatever the charge carriers are emitted by the source to allowing the conduction in a JFET, that is passing through the drain terminal to produce the maximum drain current is allowed by the junction field effect transistor. And coming to this gate, The gate is acts as a controlling media, and based on this gate, we can control the flow of conduction across this N channel JFET or a P channel JFET. Now, similarly, if you want to construct the P channel JFET, let us consider a piece of semiconductor, and this piece of semiconductor bar is made up with a P type, and it is called as a P type channel. And one end is connected with a electrode. That electrode is represented as source. Another side, a electrode. That electrode is represented as drain. And opposite two ends is doping with a heavily doped opposite material that is compared with the channel. Hence, it is represented as N plus. And this N plus is interconnected with the P channel. It forms one junction. And internally, these two are shorted. Externally, it is connected to one electrode. That electrode is represented as gate. And based on these two constructions, if you observe the N channel JFET, in N channel JFET, the source and the drain is made up with N type material, and the gate is made up with P type, but it is heavily doped compared with source and drain. Similarly, if you observe the P channel JFET, in this P channel JFET, the source and the drain terminal is made up with P type, and the gate is made up with heavily doped N material. Hence, it is represented as N plus. And if you want to allow the conduction in this P channel JFET, the conduction depends upon the majority charge carriers. If you consider this P channel JFET, the majority charge carriers are holes. Suppose if we consider the N channel JFET, the majority charge carriers are electrons. And with respect to this channel and with respect to the source and the drain, if you want to identify the behavior or the operation of either a N channel JFET or a P channel JFET, we need to apply a amount of biasing voltage between the terminals. For this case, and based on the construction principle, we need to apply a biasing between drain and source that is represented as VDS. Or means we need to find out the potential difference between drain and a source, or it is also represented as VD. A biasing is required between the drain and the source. Why? Because of that, we need to allow the charge carriers to conduct the conduction across the JFET, either in a N channel or a JFET. But the biasing is with respect to the type of material we use for either source or a drain or a gate. But why the biasing is required again between the gate and the source means to control the flow of current. That can be done through a biasing voltage is applied between gate and the source. So coming to this P channel JFET, and based on this construction, and the conduction depends upon the majority charge carriers, that is holes. Hence, the source is made up with a P type material, and the majority charge carriers are holes. And minority charge carriers are electrons. But the gate side, the majority charge carriers are electrons. So this is the source side. The majority charge carriers are electrons in N channel. Similarly, if you compare with the gate side, so the majority charge carriers are holes. Similarly, in a P channel JFET, and with respect to the source side, the source can made up with p-type material, hence the majority charge carriers are holes. If you are comparing with the gate terminal, the majority charge carriers are electron. Hence, in a p-type, the gate is made up with a heavily doped n-type material. So based on this representation of the charge carriers, we need to apply some biasing to allow the behavior of the or to identify the behavior of the this JFET, junction field effect transistor. So hence, and based on these two constructions, we identified that it contains a N type or a P type bar that is made up with silicon, and it have some ohmic contacts or terminals at the two ends, and that is called as the source and the drain. And let us consider if you are applying the N channel. Suppose if I am drawing this is a N channel JFET, means we need to take a N type bar, and this N type bar here it is also called as the N channel, and one end it is represented as the source, one end is represented as the drain, and opposite two ends is doped with a heavily doped material P plus. Internally it is shorted, externally it is K. And based on the construction principle, if we want to emit the charge carriers, we need to apply some amount of force to repel the charge carrier or to allow the conduction across the JFET. The conduction takes from the drain side, and we need to repel the charge carriers from the source to drain by using this channel. In this case, if you consider this N channel JFET, the source is made with N type, hence the majority charge carriers are electron. If you want to repel the electron from the one place to the another place, or if you want to movement the charge carriers from the one place to the another place, we need to apply some force. For this case, now we need to apply to movement this electron or to repel this charge carrier electrons or to repel this majority charge carrier. Source is made with electron, and we know that the electron is a negative charge particle. Hence, for this source side, we are going to apply a negative bias with respect to the drain side. And if a drain is biased with a positive pole, so what happens? Electron is always attracts the positive pole of the battery. And due to this force, the electrons are repelling. The electrons are repelling from the source to drain. Hence, the conventional current flows from the drain to source. So this is the current flow direction, and this is the current flow direction, and this is a electron flow direction. Due to this applied energy, electrons or a majority charge carriers are repelling from the source to drain by using this N-type bar to allow the conduction across the drain. So hence, to allow this conduction or the electrons to be, we need to apply the pairing between electrons and holes. We need to make the biasing with respect to the drain. Hence, the drain is biased with a positive pole of the battery. And due to this biasing of between the biasing voltage between the drain and the source, whatever the charge carriers are emitted from the source with respect to the force, all these charge carriers are to be attracting towards the drain side with a positive pole of the battery. Hence, the current is flowing from the drain to source. And apart from that, again we have the one more terminal is the gate. So here the gate is heavily doped P-type. If this is for a N-type bar, if you are using the N-type bar, or suppose if it is N-type silicon, that is for a P-type bar. We have the two types of the JFETs. One is N-channel JFET, another one is P-channel JFET. So hence, if you use the N-channel JFET, the gate is doped with a P-type silicon. If it is N-type silicon, then that is means if it is a P-type bar, the gate is based with N-type silicon. And based on these doping levels, it forms the one junction that is called as the PN junction. And internally, we know that that is shorted. That name is called as a gate. Apart from these three terminals, either source, drain, or a gate, a channel is established to allow the charge carriers or to repel the charge carriers from the source place to the drain place, and that region, how the movement of the charge carriers are repelling from the source to drain by using the some region. The region is called as a channel region. So now coming to you, this is a symbolic representation of N-channel JFET. So this is a piece of bar or N-type bar. This is called N-type bar. One end is connected with the drain, one end is connected with the source, and this is a diffusing material for this N-type semiconductor bar, that is nothing but a gate terminal. And similarly, if you observe the P-type symbolic representation, it shows that a P-type JFET or a P-channel JFET. So this is the channel. The channel is represented the P-type bar, and opposite two ends is doped with the N-type material that is internally shorted, that is connected to gate. Now we'll see the operation of a N-channel JFET. And so here we need to identify the behavior of the either N-channel JFET or a P-channel JFET. We need to apply some amount of the biasing between the terminals. And based on this construction and based on the representation of the terminals, we know that the source is always emits the charge carriers to allow the conduction across the drains. Hence, drain is always attracting the charge carriers from the source. Hence, we need to apply a biasing between drain and the source. And with respect to the channel, means here we consider as N-channel JFET. Hence, source is biased with the negative pole of the battery. Drain is biased with the positive pole of the battery. Hence, that is the reason. Here I applied a biasing voltage between drain and a source, that is represented as the drain is connected to positive pole of the battery, and similarly the source is connected to negative pole of the battery. At this point, and again, why the biasing voltage is required between the gate and the source, again why it is only the negative is required, we will discuss later. Why? Because of a negative biasing is required here to control the flow of drain current. Actually here the gate voltage is we connected as a negative. Due to this negative gate voltage, it controls the flow of drain current from the drain to source term. So we'll discuss in detail why it is biased with the negative. Before going to understand this principle, if you take the normal PN junction, let us take a normal PN junction. Means this is, let's take the P-type bar and the N-type. If your P is connected with the positive pole of the battery and the N is connected with the negative pole of the battery, then we can say that this particular junction becomes forward bias. If it is a forward bias, we know that the depletion region becomes very narrow. Depletion region becomes very narrow, decreasing. Whenever the particular PN junction is reverse bias, means the P is connected to negative pole of the battery and N is connected to positive pole of the battery, this particular junction acts as a reverse bias. And we know that under this reverse bias, the depletion region or the depletion width is increases. A large depletion width is established between the P-type material and the N-type material. And we know that when the large depletion width is established, there is no movement of the charge carriers from the one region to the another region, hence there is no conduction takes place across the particular PN. So to apply this principle for this JFET to control the flow of drain current from the drain to the means, if you want to limit the flow of current, that can be done through a biasing voltage between the gate and the source as well as the drain and the source. Hence, we require the two biasing voltages. One is between the drain and the source, another one is gate and the source. So let us consider what happens when the VGS is 0 and VDS is 0. Suppose if I am taking this one, this is here I represented the N channel JFET, and this is my N channel JFET, drain side and source. This is P plus. So what is the meaning? When VGS is 0 and the VDS is 0 means drain to source, the voltage source is 0 means short circuited. Similarly, gate is also short circuited. This is gate. So internally these two are shorted. And now we are applying a 0 voltage across the source. Hence what happens? So we are not applying any force to repel the charge carrier from the source to drain. Under this condition, and there is no movement of the charge carriers from the source to drain, hence it does not allow any flow of current from the drain to source. Under this point, the drain current is represented as 0. So ID means here it is represented as drain current. So it is represented as drain current. Why? Because of the force, whatever the force we are applying, the external force, either between drain and the source as well as the gate and the source, we consider as 0. And due to this 0 force, there is no movement or repelling the charge carriers from the source to drain. So here the repel charge carriers means the majority charge carriers, and based on this N-type silicon bar, the majority charge carriers are electrons, means none of the electron is repelling from the source to drain, hence it does not allow the flow of conduction across the drain to source. Under this point, the drain current is represented as 0, and this state is also represented as non-conduction state. Under this point, the JFET is called as a non-conducting state. Now we'll see what happens again when VDS is 0 and again VGS is decreased from 0. So to allow the means to control the flow of current between drain and the source, already we know that the gate is biased with a reverse voltage. Hence, if you are increasing the reverse voltage, then what happens we'll see. So that increasing the reverse voltage is nothing but a VGS is decreased from 0, means the reverse voltage is increases. Under this condition, let us consider again a N-channel JFET. So here I am going to take a N-type bar, and this is drain, source, and this is P-type heavily doped material. This is the N bar. Internally these two are shorted. It is connected to gate. Now I am going to apply a VDS is 0, means between drain and the source the biasing voltage is 0, hence it is a short circuited. And the VGS is decreased from 0, means gate voltage. I am going to apply the reverse voltage. Now this voltage is VGS is increases, or means VGS is increases means reverse voltage is increases. If the reverse voltage is increases, means that is decreasing from the 0. And at this point, now see what happens. And here there is no force between the source and the drain, hence there is no movement of the charge carriers from the one place to the another or source to drain. Hence, there is no conduction again takes place from the drain to source. And for this case, now we apply a reverse voltage between gate and the source. If you observe that this construction of the N channel JFET and the gate is made with P plus material. So for this P type material, if you apply the negative pole of the battery, this particular junction becomes reverse bias. Hence, the depletion layer width increases. So like this, depletion width increases towards the opposite sides. If it goes on increasing this reverse voltage, so what happens? Depletion width, at very large reverse voltage, the depletion width becomes very large. At particular point, the two depletion widths of internal layer are to be shorted. Hence, the channel should be disappear. Means, and that state here it is called as, at this point the channel state is called as the cutoff. Means, so when it goes on increasing the reverse voltage between the gate and the source internally due to the formation of these junctions, the depletion widths increases. At very large reverse voltage, the depletion widths becomes shorted, hence it disappears the channel region or a channel width. So the channel width is a disappear means there is no movement of the charge carriers from the means there is no path to reach the charge carrier means it completely occupies the charge channel. Due to this large reverse voltage, it completely occupies the channel width or channel region. Hence, there is no path to movement the charge carriers from the source to drain. At this point, this particular state is again called as a cutoff state. So hence again the drain current is also represented as 0. So hence to allow from these two observations, if VDS is a 0, there is no movement of the charge carriers from the source to drain, even though when VGS is a 0. When again in the second point we assume that again VDS is a 0. If a VGS is decreased from 0 also, there is no movement of the charge carriers from the one region to the another region. Hence, from these two observations, if you want to allow the movement, means if you want to allow the amount of conduction in a particular JFET, so here I am talking about N channel JFET. In this case, at least we need to apply some amount of the biasing voltage between the drain and the source. Then it can be allowed to repel the charge carriers from the source to drain. Hence, the drain current is the flows from drain to source. Hence, now I'm going to change when VGS is a 0 and VDS is increased from 0. So for this case, again, let us consider a N-type bar. This is N-type bar, or it is also called as N channel. One side, the electrode is represented as a source. Another side, the electrode is represented as a drain, and internally two opposites heavily doped material that is called as P plus, and internally these two are shorted, it is connected to gate. Now I'm going to apply a biasing voltage is increased from 0 between drain and the source. Hence, we know that drain is a biased with the positive pole of the battery and the source is a biased with the negative pole of the battery. Now I'm going to increase this one, but I applied the biasing voltage between the gate and the source is 0. Hence, gate and the source terminals are shorted. And at this point, if a gate and a source is shorted, internally it has a small depletion width between the two opposites N. And this is the maximum area to allow the charge carriers from the source to drain. With respect to this biasing voltage between the drain and the source, and we know that here the source is made up with N-type material, hence the source is biased with the negative pole of the battery. Due to this negative energy, the majority charge carriers in this source, that is electrons, the electrons are repelled from this source to drain by using this region. The region is nothing but a channel. If a charge carriers are repelling from the source place to the drain place and those to be attracting towards a positive. Hence, a conventional loop will be exit, means all the charge carriers are repelling from the source to drain towards the battery, first to pull the battery like that. Hence, a conventional current, that is nothing but a drain current. The drain current means that is represented as ID. So due to this, so we know that the electron flow direction and the current flow direction is opposite. Hence, the electron is a repelling or a movementing from the source to drain. Hence, the conventional current is a flows from drain to source. And how much current is a flows, that is depends upon these are the properties. So that is one is the number of majority charge carriers. So here I consider the N channel. Hence, here the majority charge carriers are electron. So how many charge carriers are there in this channel? And then based on the number of charge carriers, hence the conductivity is a difference. And along with the length of the channel. So we consider some piece of the bar. And the conduction is also depends upon the length of the channel as well as the cross-sectional area of the channel at B. So means this is some cross-sectional area. And this is the length of the channel. So this is length and this is cross-sectional area. So hence, the conduction, even though if you apply the biasing voltage between the drain and the source, that conductivity or how much current is flows from drain to source, that is depends upon the based on the majority charge carriers of the channel as well as the length of the channel and the cross-sectional area of the channel. From these 3 points, and here the magnitude or the resistivity of the channel R is represented as rho L by A. So means L is the length of the channel, A means area of the cross-sectional area of the channel, and this is the resistivity or a constant permittivity. And from that, if you want to identify that the drain current, generally we know that the current is I is a V by R. So this drain current is allowed with respect to the applied biasing voltage between the drain and the source. Hence, it is represented as VDS to the R. But here, R is the resistivity that depends upon these 3 parameters, rho L by A, where L is the length of the channel, A is the cross-sectional area. You can substitute this R here. Now ID becomes, this is A times of VDS by rho L. So due to this factor, the drain current is flows from the drain to source. Now, based on this condition, if you want to, so this is the maximum drain current. So if you observe this current, ID is directly proportional to area as well as the biasing voltage. And this ID is inversely proportional to the length of the channel. So, and from these 2 observations, and the drain current is directly proportional to the biasing voltage is applied between the drain and source. Means how much force we applied between the drain and the source, the amount of the charge carriers are repelling from the source to drain to allow the drain current from the drain to source. If you want to limit this flow of current, we know that if a VDS is a maximum, then from this representation, the drain current is also becomes maximum. If you want to limit this flow of current or if you want to control this flow of drain current, and here we need to apply a biasing voltage between the gate and the source. If you observe this representation, now if you want to control this, means this is N type bar, this is N bar. Now, if we want to control the flow of current, means we need to increase this depletion layers. So here we need to increase the depletion widths between these two heavily doped material. To increase this depletion width means what happens? The cross, it means here the flow of charge carriers concentration rate will be decreased. Means this will be becomes very narrow. To widening of the depletion width. To widening of this depletion width, that can be done through a reverse biasing. Hence, the gate is biased with a negative polar for this N channel. If it is the P channel, the gate is biased with a positive polar of the battery to control the flow of current. So that is the reason the FET is called as the field effect transistor. Means how much energy we applied between the drain and the source and the gate and source. With respect to this field, it allows the flow of current, hence it is called as the field effect transistor. To understand this principle, I given one simple example. If a tap is fitted with a valve, so in this case, let us consider a tap is fitted with a valve, and here this is called, it is acts as the gate, and let us take this is source, and this is the drain, this side. And here the drain current is depends upon gate also. So here I am showing that. So when valve is fully closed, so means valve is fully tightened, what happens? Even though if you are applying the source, means there is no movement of the water flow from source to drain. Hence, there is no water flows. Means that even though we are applying the biasing voltage between the source and the drain, but if a very large reverse voltage is applied across the gate terminal, and we observe that with very large reverse voltage, what happens? It increases the large depletion width between the two regions. Hence, at very large reverse voltage, it completely occupies the channel. If it is completely occupied the channel, there is no path to share the charge to reach the charge carrier from the source to drain. Hence, the drain current is represented as 0. Similarly, if a valve is partially open, means a very small, so if a voltage is decreasing, what happens? The water flow is also less here. If you want to allow the maximum force, means gate is completely open. Here the gate is completely open, means the gate voltage VGS is a 0. When the VGS is a 0, means that is nothing but this is gate, and here this is the source, and this is drain. So when the gate is completely open, that is nothing but a VGS is a 0. If a VGS is 0, means it having a very internal depletion width, means so due to that the maximum area will be occurred between this channel. Due to that, a maximum flow will be flows from a source to drain, or the maximum current is the flows from drain to source. Hence, here the water flow will be with full force. So from these three observations, means to control the flow of drain current, that can be, so from these three examples we identify that if you want to control the flow of water, that can be done through a valve. Similarly, in a JFET, a junction field effect transistor, if you want to control the flow of drain current, that should be controlled with respect to the applied biasing voltage between the gate and the source. And that reverse biasing voltage between the gate and the source is control the flow of drain and source. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.